So the past 2 days we've only been looking at angles that are on the unit circle, or coordinates that are simple coordinates, as I like to call them. They are the half, the root 2 over 2, root 3 over 2, and then 0 and 1. We also put 0 first, but 1 and then 0. These are the easy coordinates that we have, just because they're defined by some of our angles. So like the cosine, this would be, so the angle-wise, this would be 0. This would be pi over 2. Root 3 over 2 is pi over 6. Root 2 over 2 is over pi over 4. And then the half is pi over 3. Today we're going to be looking at solving for any coordinate. We're only going to be looking at cases such as sine inverse of something. So we're always going to have sine inverse on the inside of our brackets for today, just because otherwise we can't really do too much this time. So it's just nicer about finding the exact value. We need to have a coordinate for that. Can someone remind me of what the output is of an inverse function?
The reflection of
The what?
is it basically like a reflection?
The output. So like, if I'm given x, what does x represent for sine inverse?
Like the y.
This is the y coordinate. So what would sine inverse equal?
I'm not sure.
So I'll call them one real quick. So I tell you sine inverse the half, right? You would look at it and you say, oh, well, this is root 3 over 2, comma, half. So here's my coordinate. What does sine inverse come? Tells me this portion, right, which is the angle. So my input is a coordinate, my output is always an angle. We're missing this theta here. That is not a theta over the kinetic case of that y. So we know this works because then sine has to have an angle as an input, which is fine because sine inverse gives us an angle as an output. So that's why we can do things like sine inverse, is because the output of sine inverse is an appropriate input for sine. So we're going to start by looking at sine inverse of 2/3. The 2/3 is not one of our nice coordinates, but we do know two pieces of information from this 2/3. What is sine as a fraction? What over what?
It's opposite over hypotenuse.
Opposite over hypotenuse, that works as well, so it's going to be drawing the right triangle, which is 3. It's also our y over r. So I'm going to start by drawing some coordinates. What quadrant would 2/3 be in? You know, it's going to be quadrant 1 or 4, so is it positive or negative 2/3?
1.
You're going to quadrant 1 with the positive, yep. So I know I'm going to be going up 2, and then my radius is 3. Now when we deal with inverse functions, we're always getting our angle. When we're dealing with the unit circle, we always draw our angle from the origin. So the angle we care about is here. That's why I wrote the 2 as horizontal there. What's nice is we don't actually need to find what this number is. We don't care what theta is equal to. We only care that we are going to get a theta from sine inverse. So we do. So I'm not going to treat this as sine of theta. So what would sine of theta be in this problem?
2/3.
So this is 2/3. This is actually a copy that we saw yesterday as well, where what we did was we knew well sine of sine inverse of f is equal to x if x is in the domain of sine inverse, so -1, that's x. So this one was just using our property, but now if we wanted, we could also go and find, so when we don't have the ability to use identities, if I have cosine of sine inverse of 2/3, I already have the right triangle drawn. I already have my sine of 2/3, so here's my y, here's my radius. How would I find cosine of theta? So what would be the fraction for cosine of theta?
This is the hypotenuse.
It would be the adjacent of the hypotenuse. Do we know our adjacent right now?
No.
I'm going to this A. How would we find our adjacent side?
Do we have an angle yet?
We don't need it. The only thing we need to know is where theta is. We can find A without needing to use any equation.
Would that be Pythagorean?
It would be Pythagorean.
I forgot about that. Yeah.
So Pythagoras tells us what plus what equals what.
It's supposed to be 44
A squared plus, I'm going to write b as 2 squared is equal to 3 squared. And a squared is equal to 4, or plus 4 equals 9.
9.
And then I would need to subtract 4 from both sides. That has a squared is equal to 5, so a is equal to plus or minus square root of 5. What quadrant though are we in? We're in quadrant 1, so a has to be positive or negative.
Positive.
Now what's cool about this actually is when we're dealing with our inverse functions, what would a be if we were in quadrant 4?
Negative square root of 5?
So if I were to go draw this down here, let me switch to
Wait, what's the
I think I just heard someone say it.
Yeah, what's the positive?
It'd be positive. A hasn't moved. It's still in quadrant 1 and 4.
Oh.
Yeah, this is still a positive. It doesn't change. Yes, it does follow from that as well. So the idea of all things equal. So in quadrant 4, cosine is positive. We now have a value for our adjacent. We got that square root of 5, and we already knew hypotenuse on our sine inverse function. So we have cosine of theta. Well, actually, I can even go back and say cosine of sine inverse of 2/3 is equal to square root of 5 over 3. Yeah.
Where did the cosine come from?
This was a new problem. So this was, here's number 1. Here's number 2. So number 1 was looking at setting up a right triangle and getting our identity from before, like on yesterday. Number 2 was, well, now we can't use our identity because we have cosines and numbers within different. Okay. We have really today is just all examples, honestly. So we're going to look at a few more without any new identities, and then we'll move on to with identities. Number 3. So for number 3 we have sine, cosine, inverse of 1/3. So to recall, we know we're going to have an angle that is between 0 and pi from cosine inverse. Okay, so our first question is always going to be what quadrant is 1/3 in? First, so my 1 is representing my x, and then over 1.
Oh, that's what that is.
Yep. So since cosine is x over r, the 1 represents my x value, the 3 represents the radius. This is 3, this is 1. I know that I always draw my angle from the origin. So the only thing I'm now missing for sine, what do I need?
Opposite.
I need my opposite, which I don't know. So I need sine of theta is equal to opposite over 3. How would I find my opposite?
Look further to always further.
So without a theta, how could I find my missing value?
1 squared.
Yep.
Plus,
And we're going to call it a squared.
1 squared plus a squared equals 3 squared. Oh,
The 1 is super
yeah,
small. So then, step 1 should always be sketching it, step 2 should always be painting it. So then this is going to give us a squared is equal to 8. A is equal to, since we're in quadrant 1, this is going to be a positive square root of 8. What quadrant does cosine care about?
4.
So step 1 is always sketching our triangle based on our coordinates. Step 2 is using pi sag to get the missing side. For cosine, we know cosine can depend from 0 to pi. It only cares about quadrants 1 and 2. And we know in quadrants 1 and 2, sine will always be positive because my y is positive. So what's nice is whenever we're working with just sine and cosine, we're always going to get positive answers. We saw with cosine, we're going to have quadrants 1 and 4, cosine positive 1 and 4. For sine on the outside, we have quadrants 1 and 2, and sine is positive. So 3 is just plug in. So we get our answer as opposite is root 8 over 3. Alright. Just a moment, we'll keep the copy. We could also work, say, with tan inverse. We could work with tangent on the outside, we're going to see tangent on the outside of the next one. As long as we're given really a cosine, so as long as we're doing an inverse on the inside, we know two coordinates. And if we know two coordinates, like two really sides, I should say, we can find the missing side to solve for an angle exactly. Not using a trig identity, but using the proportions. So I can draw on this line. Right. We're going to do a I'll switch that one. Okay, so with these, we can extend properties as well. So this is now applying properties. So everything up to 6.5 has given us different identities we can use to help us solve problems. I'm going to quickly look at cosine, sine inverse, 3/5 plus tan inverse of 1. Okay. So this one you might think is a lot different and much more difficult. It's not. It's the same steps. I'm going to rewrite this in red really quick in a more familiar form, which is just cosine of A plus B. So this is going back to our sum identity for cosine, where A is just going to be sine inverse of 3/5, and B will be tan inverse of 1. Does anyone remember the identity for the cosine sum?
I think it was cosine, cosine A plus B over B.
Cosine of A is going to be cosine A cosine B. And then with cosine, so for the sum, it's always something times something. Cosine, since it's even, it's the same. So it's going to be cosine A cosine B, but cosine switches sign. So it's going to be minus sine A sine B. I can now go back and just plug in my A's and B's. So it's going to be cosine of sine inverse 3/5 times cosine tan inverse of 1 minus sine inverse 3/5 and sine tangent inverse of 1. Then what I do is I just go and draw. So I first apply my identities, first use identities, and then our second step becomes to draw this one, 2. So step 2 is now called triangles.
You gotta draw triangles for all 4 of them?
You don't know. So we only care about right now. So sine of 3/5. We only have to do 2. So sine of 3/5 is the same as sine inverse of 3/5.
Oh yeah.
And then the tangent inverse is the same distance. We only have to do 2, and then we'll be good. Quickly make a sketch. So sine tells me my opposite, which is my y. So I'm going to have 3 as my y and 5 as my hypotenuse. And then this is sine inverse. And then tangent inverse. So this isn't quite in the form we should recognize maybe right away. Tangent, if you recall, is y over x. Since this is 1, I'm just going to make our life easier and say this is 1 over 1. So then my triangle would be, well, positive 1 and positive 1. There's 1, there's 1. I would then use Pythagorean theorem, so I'd have 5 squared is equal to a squared plus 3 squared. And over here I have 1 squared plus 1 squared is equal to 2 squared. Radiuses are always positive, so tan inverse and then get square root of 2 to go to c. And then over here I'll have 25 equals a plus 9. So I'll have a squared. So a squared is equal to 16. So this is actually a 3 plus 5 triangle, so a is just 4. Okay. From here, I now have everything I need to know. So how would I find, so the first I'm looking at is cosine sine inverse equation. What would cosine be in this first triangle?
Well,
So I'm going to label this in green. Here's my green triangle.
would it be 3 over 5?
You're giving me sine. What would cosine be?
4 over 5.
4 over 5. So cosine is adjacent. So this is 4/5. And then sine. What's cosine of tangent inverse of 1? So in my red graph, what would cosine be?
1 over 1.
1 over square root of 2.
Okay.
Then I have minus. What would sine of sine inverse of 3/5 do?
3.
You're going to need a cosecant.
Okay.
You want opposite of a hypotenuse, which is 3 over 5.
Oh, okay.
This one actually falls from our inverse identity that we looked at 2 days ago. And then what would sine of tangent inverse be? So what would sine be in the red graph?
1 over square root of 2.
1 over square root of 2. Good. And then from here, it's just multiplying everything through. So this is 4 over 5 root 2 minus 3 over 5 root 2. We have a common denominator, so we can actually combine these. This is 1 over 5 root 2. And then to avoid having a radical in the denominator, we multiply by 1, which is root 2 over root 2. So we get root 2 over 5 times 2, which is equal to root 2 over 10. So these ones are longer, but the idea is still the same. You're still just checking each essentially part. So we're saying, well, this is its own problem that we did before. It's just cosine of some inverse of 3/5. So you're doing each problem individually and then multiplying through to get your final answer. Done here?
Yeah, I was going to ask that.
Yep, so this is equal to square root of 2 over 5. I have square root of 2 times square root of 2, so this is square root of 2 squared. The square root squared is the number in red.
Mr. Bennett.
Yeah.
So would it be right if you left it at 1 over 5 square root of 2?
I particularly won't care. In the future, some people will be very picky about it. It's not good mathematical discourse to have a radical in the denominator, but it's still technically conveying the same information. So on a technicality, that's fine, but some people will not accept it.
How about the final?
The final concept poster, they would not. So like that'd be an example of where I'm more relaxed about it, but I would specifically, if I were to give you something that can make sure if on a homework you're not doing it, that's fine, but if on a test, I would specifically say make sure to put make sure to simplify include moving radicals out of the numbers. So like on your final it says simplify solution. Okay, we just have one more example that uses identity, and then we are all set for the day. Here we go. And then just a reminder, tomorrow all you're doing is the homework for this section. I'll have the office hours like I did on Monday. I can extend those later in case people have like schedules that are busier in the morning. So really, if you send me a reasonable time up to like 6:30, maybe half an hour, you can accommodate that. So sign. But then I'll have 2 sessions that are half hours during like the normal the actual 3 of them. That's sine, cosine, inverse of 3/6 plus tan inverse of 1. Okay. Does anyone recall the identity for, so I'm going to quickly label these as A and B. Here's my A. Here's my B. So this is really just sine of A plus B. Does anyone recall the identity for the sine sum?
Sine A, sine B, sine A, cosine B.
Sine A, cosine B, yep.
Yeah.
And then, so I like to think of, technically that's not the best reason, but I like to think of odd and even functions in terms of like positive and negative, or even odd and even, like an even you can get by multiplying an even and even, so those are the same. That's how I kind of recall odd, or how I call cosine. I do the positive and negative idea. So if even, it's positive, it means it matches. If it's odd, it's negative, meaning they're different. So evens are the same, odds are different for functions. So it's sine A, cosine B, sine each the sum, and then it's going to be sine B cosine A. Okay. So now we just need to make our graphs, and that's going to be these same colors this time. So for cosine, we're given an x over a radius. So my x is going to be 3. My radius is 5. What kind of triangle do we have?
3, 4, 5.
So 3, 4, 5. So this is just 4. And then that's going to be a different color for blue, so it's just yellow and also this blue. And then we actually already have this graph, so I'm just going to skip right through this. This is tan inverse of 1 again. So this is a 1, 1 square root 6. We then just do exactly what we did before. We re-plug our A and B back in, having solved each piece. So I have sine, cosine inverse 3/5, cosine, tan inverse of 1, plus sine tan inverse of 1, cosine inverse of 3/6. What is sine in our red graph?
4/5.
4/5. This is 4/5. What is cosine in our pink graph?
1/square root of 2.
Yep. Then we have the sum. Then we have sine of tan inverse equals to 1/square root of 2. And then we don't actually even need to use our graph for this one because right now we have an identity. 3/5 is between -1 and 1. So this is just 3/5. I'm going to make this out. And then all we need to do is multiply through. So 4 times 1 is 4, and then 5 times 2. Then we have plus 1 times 3 is 3, then 5 times 2. We now have 7 over 5 root 2. And then this is going to be the same process as we had before, where we multiply by root 2 over root 2. We get that this is going to cancel out the root. So we could do 7 square root of 2 all over 10. So every problem from this portion of 6.5 on is repetitive in the sense that if there's an identity, first do the identity, and that's going to write 6 over to the side 6 after the copy.
Is this what our homework on?
Your homework is on everything from 6.5. So using the inverse identity from for sine inverse and cosine inverse, and then this. So what we just did today is like a third of the homework, a third of it is on sine, a third of it is on the cosine. So that. So apply identity. Step 2 is draw triangles. Uh, 3 is find the missing pieces. And then 4 is log the plane.